you're at the Lucene Spatial Deep Dive. I'm Dave Smiley. I work at MITRE. Been at MITRE for my professional life, basically. Working with Solr and Endeca. I've become sort of a mini solar consultant within a large company, working for MITRE and our sponsors, our government sponsors. We're a nonprofit, kind of an interesting company. I have published those two books up there. There's the first edition and the second edition. I'm working on the third. It's a ton of work. Even though it's just an update, you'd be surprised. I also have 2 kids now, and when I wrote the first one, I didn't have any kids. That's a big difference. So I presented at conferences before. I've also done some solar training. So I've broken this down into some tidy subject areas. It's not a big mess. I'm going to be talking about some background about spatial search. Then I'm going to cover spatial for J, which is one subject. Then Lucene Spatial, which uses spatial for J. And in particular, I'm going to draw a lot of attention to a particular aspect of Lucene Spatial that has to do with prefix-tree implementation. And then I'm going to talk about Solr Spatial, which is how many of you might ultimately see all of this, depending on what level you choose to integrate. And then do a little demo. Maybe at a couple times I'll do a little demo. And then at the very end we'll talk about some interesting use cases that I found that are not boring, typical questions, but some interesting cases that cause you to kind of think a little bit about ways to solve problems. What is spatial search? For many people, I think it's really pretty simple. Many people need to basically index a point. It might be a business. They might want to say if a document represents a business and that there's a spatial field that represents where that business is, they want to know what businesses are near what businesses are near where the user is searching, for example. Pretty simple stuff. These are, I think, the kind of more typical requirements that many platforms address. The spatial code that I've been working on does a lot more than this, but for the most part, this is what many people have in mind. It's not, when some people think spatial search, they think, oh, so when I type in the word Boston, it knows that's Boston. That's a different kind of thing. Some people call that geocoding. There's other solutions out there that will take your search query, if it's intended to be a location, and figure out where that is. That's not what I'm talking about here. That's another thing. I think there's, about to mention an open source project that actually does that, and I forgot the name of it offhand. Anyway, so a little background of this on the subject. When I first was writing the first Solr book, at that time, something called Local Lucene was out by Patrick O'Leary, who worked for AOL. And there was a Lucene level plugin of sorts. I think there was a Solr adaptation of it. So at the time, it seemed relatively successful in terms of there was someone who developed something rather sophisticated. It was initially an external third-party plugin. Eventually, it became the Lucene Spatial contrib module. So things seem successful and wonderful so far. However, he didn't have time to work on it anymore, and it had some bugs, and no one can seem to figure out why these bugs were there. So it became this sort of abandoned spatial contrib module that seemed to work okay in North America, and if you go outside of there, maybe not. Then there was somebody named Chris Mail. Presently, I am each other from time to time because we work in the kind of the spatial sphere of work. At the time, he worked for JTeam. That was then renamed to Orange 11. That was probably bought by somebody else. But anyway, so there's something called the Spatial Solar Search plugin. That's a bit old at this point. That was for Solr 3, and it was somewhat based on Patrick's work, but it fixed certain bugs. And about a year later, I was working on a project for my sponsor, and we needed to index a variable number of points per document, a variable number. And the existing spatial options out there did not do that. So I needed to come up with something. So I was looking at geohashes, and that was very interesting to me. And I realized that I could implement something here. And so the first Lucene Revolution, I presented my approach, and it has evolved since then. So that's when I got involved back then. So there are three of us here. There's another person, Ryan McKinley, who works for Voyager GIS. So he, Chris Mail, and myself, we kind of got together and we thought that we'd put our efforts together in creating something comprehensive and cohesive that addressed a variety of use cases. So we worked together on something called, under the name Lucene Spatial Playground. It was sort of a working name. No one was supposed to know about it, but then people start knowing about it and people start saying LSP, this and that. And LSP technically doesn't exist anymore, but unfortunately still people hear it. People still say it. And then not that long after we started that, Solr 3.1 came out, and it was the first Solr release to have direct spatial support itself. Primarily done, as far as I can tell, by Grant and Yannick, did different parts of it. And about a year ago, basically, LSP, more or less, parts of it became the new Lucene Spatial module. Some of it became an independent project called Spatial4J, and the rest of it went off, that didn't really belong in those two buckets very well, went off into just a GitHub project that Ryan has called Spatial Solr Playground. Here's all of us. We're across the globe. At times it can be interesting because Chris I speak to him late at night and early in the morning, I am, but not in the middle of the day because that's when he's asleep, and vice versa from his experience. And Ryan's on the West Coast and I'm on the East Coast, so it's sort of interesting. The reality is that right now, Ryan kind of brought us together a bit, but Chris left Elasticsearch and he's doing other things. And Ryan has bursts of activity, so lately he hasn't been as involved, but at least we talked together about how to approach a problem, even though he doesn't have time to actually work on solving those problems, but at least we collaborate on how to address certain things. So if we were to take all this spatial stuff and kind of decompose it into logical pieces, at the base layer, there's something called Spatial4J, which is all about shapes. That's all it is. It's just shapes. I have a little section on Spatial4J in more detail, but just understand right now that it's basically where there's a shape abstraction. You got circles and rectangles and ways of dealing with polygons, etc. Then there's Lucene Spatial. So Spatial4J, by the way, doesn't index shapes. Spatial4J is just some classes, if you will, with some basic operations that you can do on them. And it, aside from an optional dependency on JTS, it otherwise doesn't have any dependencies. Then there's Lucene Spatial, which obviously depends on Lucene, and its primary job is to index and search these shapes, and it uses Spatial4J for the shape implementations. Then there's, on top of that, then there's the Solr side. And in this case, Solr is really somewhat of a thin adapter on top of most of the work, which is on lower layers. And on the side, there's some other stuff that's on a GitHub project, Spatial Solr Sandbox. I don't use that term very much, but it's just a GitHub project for some miscellaneous stragglers. If you were to look at this in terms of lines of code and break it down, I think this is a nice picture because it gives you a sense of where's the meat of all this stuff. And surprisingly enough, a lot of it is in Spatial4J, more so than you might think. If you consider it's just shapes, how much could there possibly be? You'd be surprised. Well, I'm already stealing content from a slide or two away from now. But so I'd say it's pretty much equal between Spatial4J and Lucene Spatial. And although I didn't include tests within these counts, the ratios are roughly the same, but there's a lot of tests in Spatial4J and Lucene Spatial in particular, a lot. In fact, half of my time, I'd say, has to do with testing than it has to do with making something work. And here I want to give a plug, actually, for Caret Search randomized testing. The testing framework, the testing infrastructure of Lucene and Solr is really good. It's based on, it uses something called randomized testing, which is Dawood Weiss. He's a committer, and he is he's not only, it kind of came out of Lucene and Solr, really wanting much better randomized testing. And what randomized testing is, his library is all well and good, but it's really more of a philosophy about testing than it is about this particular library that I'm drawing attention to here. It's really about how do you go about writing tests. This has been a big deal for me in terms of how I think about testing, especially, again, on spatial subjects. It's used extensively. And what this is really all about is, all the library does is it gives you a random a random object that you can then call getInt or getDouble or whatever. But it makes it easy to make your test repeatable, because if it's always random, then if your test fails, how do you redo the test and get the same seed, right? So it makes it convenient to tell you what the seed is. It also gives you some utilities. But if you fully embrace this in your testing, then you can find bugs. I mean, the thing about a more typical JUnit test bug is that you might have, oh, I'm going to test that I've got this rectangle over here. Does it intersect this circle? And if you're literally writing that statically, like you're literally creating the circle and the rectangle with constant values right there, I mean, if it works, it's going to work the first time, and you're not going to be aware of edge cases that might exist. You might have some edge cases in mind. You might create some particular tests for particular cases that you think you want to make sure that it covers. But there could be all sorts of interesting edge cases in your code that you wouldn't know about because your particular static tests didn't cover. So I'm a big believer in randomized testing, and a good part of Lucene and Solr itself has fully embraced the philosophy that I have here, because I've caught some weird bugs. And actually, I was thinking about, who do I want to have to give away a book here? There's some clever logic scenarios that I never thought about until randomized testing caught cases that I thought seemed like, you got to be kidding me. In particular, I was working on cases where a rectangle, under what scenarios is the rectangle fully within the circle? Okay, now think about this in terms of a geodetic scenario, a sphere. Okay, imagine a circle on a sphere, so there's a point radius on the globe, and imagine a latitude longitude rectangle. Okay, so this is a quiz question to anybody here. Under what circumstances could all four corners of the rectangle be within the circle, yet this rectangle is not completely within the circle? Okay, so again, we've got a circle and we've got a rectangle. All four corners of this rectangle are within the circle, yet the rectangle is not completely within the circle. How could that be? I was like, how could that be when the test failed?
Could it actually be, instead of being inside the circle, it wraps the entire sphere?
Yes. You got this after, so see you after. There's another case too. Can anybody think of another case? I think that's what she said, I think. There's another even trickier case. No, it's not an elliptical thing. Here's what happens: is if the circle if it covers a pole, if you look at what that looks like when a projected space, you get, instead of looking at a circle or an ellipse of some kind, you end up with this wavy thing across the top of the pole. Like it comes down at one part and it comes up a little bit, and then it comes deeper on another part. So you could have a rectangle that spans. It's tricky to describe, but you could have a rectangle that kind of spans from one part across the other. It's a bizarre case, but it could happen. So these are cases where randomized testing, I wouldn't have thought of that, honestly. And I have a lot more faith in what randomized testing can do. I don't, it's not like everybody's testing should necessarily fully embrace this, because some things are more suitable to this than others. I think it's very suitable for the spatial kind of stuff. If you have tests for a user interface where people type in certain things and you've got some Selenium tests, that there's less applicability here, but there's great applicability for this types of thorough randomized testing. It makes writing these tests very hard, because instead of looking at static cases, did it work, you're looking at when there's a test failure, debugging it is sometimes a half-day event. But I have but it has given me confidence, and I hope you confidence that this stuff works. Anyway, spatial for J. If there was a tagline, it would be it's all about the shapes, because that's what spatial for J is all about. In hindsight, shape for J may have been a better name. I think it was Ryan chose the name, but whatever. So it's principally about shapes. There's a shape abstraction. I'm going to show you what that is in the next slide. There's a concept here is also that there's a spatial context, which is an abstraction in spatial for J that basically says, are we working in a geodetic environment, or are we working in a Cartesian flat plane kind of environment? Because there's different people who want spatial. Sometimes they don't want it geodetic. They don't want a sphere. They just want, they either have projected geospatial data, or they're using time ranges or something interesting. So there's that concept there. And a a big part of these shapes, it's not like they're just structs that hold, you know, the coordinates and then that's it. If that's all there was to it, there'd be no reason for an external library for something that simple. The big part of what they do is that they compute relationships between each other, in particular points in rectangles. So every shape needs to know the relationship it has with another rectangle. Like, is it contains within, disjoint, intersects? Very important. And that's can be pretty hard for some complex shapes. Some distance or some utilities in there. Another big thing that it does is it parses WKT. The reality is that right now it uses JTS to parse WKT, but I'm working on parsing WKT as something that's built into Spatial for J. Because once I do that, then I have a lot more flexibility in supporting making, because what if you make a new shape, like a donut shape? You'd like to be able to declare a name for that shape and what its parameters are, and then you could create it as a composite of other shapes, as a this minus that kind of shape. So it uses Java Topology Suite, JTS, for basically for polygons and basically anything in the full breadth of WKT is supported by JTS, and I've had to wrap JTS. It's not so that it supports dateline wrap as well. I basically do some clever shifting across the dateline if I see it crosses it. It's important to .NET. So I do want to point out, like, why does Spatial for J exist? I feel like I need to make the case for it. The first reaction, if I were to tell myself that this stuff would be in its own project, if I was telling me a couple years, 3 years ago or 4 years ago, like, really? You know, because at the time my circle wasn't that complicated. It was before I was aware of, you know, big ass circles with rectangles, corner. You know, these cases I wasn't yet embracing randomized testing to know how hard some of these can actually be. So you'd be surprised at how much code there can actually be behind this stuff, especially if you add the tests. Another bigger question is, why isn't it a part of Lucene Spatial? Well, basically it has to do, there's a couple reasons. One of them is its relationship with JTS, which is LGPL. I have no problems using LGPL libraries, but if you take a very strict interpretation of ASL, you might be uncomfortable. So some people fall on different sides of that line. So it was established at some point in time that Lucene was not going to have a dependency on an LGPL code. So, but it can depend on an ASL license project, which in turn does have that, and that project is not an ASF project. Hence this thing is independent. Theoretically, Spatial for J is independently useful. In reality, it's only used by Lucene Spatial right now. That may be changing soon with people I know at work, but I don't like to duplicate other code. I like to look out to see what's out there that does something that I want to do. I mean, as there's so much rich open source out there, why do you want to reinvent the wheel? In some cases, I just never found. I just didn't find this is a rectangle within a geodetic circle. There were some cases that I could have looked more thoroughly maybe, but I was not finding it. And there's so much LGPL licensed code out there that spatial is not even funny. Like most spatial code out there is LGPL licensed, a lot of it. So it's kind of disappointing. The best argument for why it doesn't necessarily have to exist is that, well, you know, couldn't the JTS parts of it be Spatial for J? So it becomes this like third-party adapter wrapper around JTS. Well, that's the best argument, but the ship has sailed, and I'm happy with it being external. So it is what it is. So here's what the shape interface looks like. You can get the center of a shape. You can get the bounding box of a shape. You can ask if it has area or to calculate the area. And the big thing that you can do with a shape is that you can compute its relation to another shape. And every shape must be able to support that other shape being a point or a rectangle. Because in practice, this is used by Lucene Spatial, who's going to shove a whole bunch of rectangles at this thing and potentially a point when you get down to a certain level. So what is a spatial relation? It's an enum of 4 possible values. Disjoint, which means that the two shapes do not, if you look at the top, there's 4 examples. The shapes do not overlap at all. There's the shape at the left and the shape at the right. So you read it kind of left to right. So the current shape is disjoint with the other shape. So intersects means the current shape intersects the other shape, but is not within or contains. Those are two special types of intersection. So the current shape is a rectangle, is within the other shape, and the current shape contains the other shape. If you're into more spatial libraries out there, you may have seen something called the DE9IM matrix. This is really a simpler subset of that. Like I don't do equals, I don't do touches and some other stuff because I haven't had the need, honestly. So look at the bottom two examples where there's a rectangle and a circle. The second one from the bottom is the rectangle is within the circle. And the bottom one, the rectangle contains the circle. So here's a list of the shapes we've got. We've got a point. A line and a line string is recently added. It's not. It's committed, but it's not in the release that's in Lucene Spatial. And I've been working on it within my employer, but there's still some support needed to more fully integrate it so that you can actually use it in Solr. But anyway, so there's a line and a line string. There's also I have a concept of a buffered line string. I ultimately use these, by the way, to piece them together to create a so-called track. Imagine a path that a vehicle takes, and you have a sequence of points, and each line is not just a line. It's a buffered line. There's a path of search area, if you will. There's different ways of modeling these kinds of problems. But anyway, so it's buffered or not buffered, configurable. There's a rectangle, pretty straightforward. There's a circle. There's a aggregate of other shapes called a shape collection. And then there's a wrapper around JTS's geometry. And a geometry in JTS is like a shape in Spatial for J. So you could have a point geometry, a line string geometry, a polygon geometry, a multi-polygon geometry, etc. So that's the JTS wrapper. So if you think of these shapes in terms of what do they support, they all support the Cartesian Earth model, which is it's not an Earth model. It's a flat model where you define a left and a right bounding box and your space that you're working in. They all support that. If you say, well, what if if I were to extend that further, where my 2D space wraps around on itself? Because if you look on Google Maps, that's kind of really what you're looking at. If you go over towards Fiji, it wraps around. So most of the shapes support that. Surprisingly enough, the circle one doesn't, but the geodetic side is. I need to add some in the process of putting this together. I realized, oh yeah, I got to put some nodes in a few places I didn't think about in the past. That represents some to-dos for me. So in geodetic is, in this case, it's a spherical model. Some people say, so is it WGS84? I got that question sometimes, multiple times actually. Spatial for J does not assume WGS84 per se. It assumes, if it's geodetic, it assumes a spherical Earth model. So it's up to you to normalize if you're getting latitudes and longitudes from some device or from some third party, it's up to you to ensure that when I say this latitude and longitude, that he means the same as that latitude. It's up to you to ensure that they're all using the same, what's called a datum. But Spatial doesn't care about that. You give it latitude and longitudes, use a spherical model. Well-known text, WKT. WKT, I think, is the most broadly supported way of representing shapes across most software out there. And there's some other useful ones as well. GeoJSON is interesting and all well and good, but WKT is most broad. And so the upper right, some examples show the typical ones you'd see on, say, Wikipedia, for example. Now, within Spatial for J, there's some extensions to that, like the latitude, comma, longitude that you see in Solr. And that weird circle looks odd. WKT is all well and good, but it's got some problems. WKT does not officially have a rectangle, but there are a few very common extensions of WKT that add it. So I'm going to do that, and they call it an envelope. Another thing is that WKT doesn't have a circle. It has a circular string. If you look up the spec, it's so bizarre, nobody actually implements it as far as I know. If you look at WKT spec, it's one common theme in WKT is that all the numbers that you give it are really on the perimeter. So for a rectangle, that's all well and good. The perimeter, the box, right? If it's a polygon, you're actually giving it the vertex. Okay, pretty good. But a circle, if you think about a circle in terms of a point and a radius, but the point is not on the edge of the circle. So instead of creating an easier to use circle, no one created that. They created this bizarre circular string, which is sort of like this. So I think I'm forced to come up with some sort of extension to have a circle because WKT doesn't. Yeah. Here's a little code sample. It's common in spatial for J code to basically reference the geo constant for spatial context. That's the geodetic Earth model. If you want a Cartesian plane, then you create a new spatial context where you tell it the boundaries. You have to tell it the boundaries. It's not like it's negative double infinity or anything like that. And the context acts like a factory for creating the shapes. It's discouraged to actually new constructor a shape. You're supposed to use the factory. That being that the factory could validate arguments and do some other things. One odd thing, and I'll admit this is odd, although I don't regret it, is that distances only show up in like a couple places in this. One is the radius of a circle, and the other is the actual distances that are returned from some of the distance utilities. And it comes back in degrees. It's more common for people to want kilometers, but the moment this thing uses kilometers, like, well, but what if it's not geodetic? Okay, well, couldn't it be radians? But what does radians even make sense on a flat world? But the nice thing about saying it's degrees is that if it's Cartesian, the units of that is roughly it's basically on the same plane as the x and the y. If it's degrees based, well, the latitude is degrees, longitude is degrees. Granted, I know there's some one longitude at the pole is not the same as one at the Earth. I'm aware of that. But the numbers are in the range between 1 and 0 and 180. So the nice thing about using a distance in those terms is that the numbers are all within that same kind of space. And you just have to just a simple constant to multiply it to get it out to something else, to get it to kilometers or radians, whatever you might want. I wish this, that being said, I do think at the Solr level, there needs to be a very simple kilometers. Because if you're using it for geospatial, obviously at a high level like Solr, you don't want that kind of detail there. But that's how it works in Spatial for J. Okay, future. Very much is definitely going to happen. There's already code in progress. The WKT support, I think, is going to be central to using Spatial for J, so that you don't need JTS just because you want you want to use that syntax. I want to basically reduce the JTS dependency and add more opportunity for you to add your own custom shapes. There's some API improvements. And there actually is a branch for adding projection support. It would be nice if you could actually declare what the datum is of the data you give it, and that way it could convert it for you. That would be nice. Any questions at this point about the Spatial for J section? I'm going to get into Lucene Spatial next.
So can you go back to the previous slide?
Yeah.
So why there are two parentheses, double parentheses around it?
That is what the WKT spec says. And the reason why the WKT spec, that's a common gotcha. People forget that and you put 1. Even I'll do that. I'm like, I actually go into the debugger to get to the point. I'm like, oh yeah. The reason why is that polygons can have holes. So the polygon, the first parenthesis wraps the coordinates, but it's really, you're giving it multiple sets of rings. The first is the outer ring, and then you have an optional number of inner rings that are holes. Many people don't even have any, so that's why you end up seeing the double parentheses there. Oh, another thing is that's XY order. WKT is strictly XY order. One thing I want to say also at this point, JTS, so for polygons, you need JTS. The current implementation is not geodetic. So what that means is, I was talking to someone at lunch about this, what that means is that if you get a polygon from somewhere, where that polygon's vertices were acquired by a GPS device or something, where you're very confident that, as opposed to someone drawing on a screen on a 2D map, let's just say you actually got the polygon from real data. It's possible, because JTS doesn't know anything, the crazy thing is JTS being such a popular spatial library, it doesn't know anything about geospatial at all. So anyway, so I pull a trick here. I use it in that context, but JTS demands a valid polygon. And for a polygon to be valid, the the edge cannot back over itself. It cannot crisscross it. It has to go completely around and never overlap any vertices. But if you get the polygon vertices from actual world measurements, it's possible to construct a simple triangle, in fact, that will, not a triangle, it has to be impossible, but a polygon with more vertices than that, to get a invalid polygon, even though it was measured in a valid sense, but because of the world model that JTS is in, it's considered to be an error. In that case, what you have to do is you could either pre-process, what do I want to say? It's sort of a workaround. What you can do is you can read in the polygon in JTS a priori, and then ask JTS, is this valid? Oh, it's not. Okay, then compute what's called the convex hull of this. That may not be the right operation, but you can basically tell it to fix it. It will do a decent job of finding that little error and making that little error go away. And then it should go through fine. Oh, another last thing about that. That's a good point, too. There's the last Lucene revolution, there was a Raytheon who had polygons that he built himself using geodetic math, which is really complex. That's some real intellectual property he's got there, and I'm really hoping he open sources it. I've been encouraging him to do that, because if that happens, then, and I'm actually more optimistic now, because if he open sources that geodetic polygon, that would be the answer to this, and that would be really awesome, because I don't know of any geodetic polygon code that exists in open source, so that would be really nice. Okay, Lucene Spatial. So again, Lucene Spatial is about indexing and searching these shapes. A key concept is that there isn't one way to do it. There's different approaches to index and search spatial based on what you want, what features you're looking for. I think there's one particular implementation I think it's great, it's useful for many cases, but it's not, there are other cases. So, what are you indexing? If you're just indexing points, or do you need to index other shapes? And there's one solution that can work if you're just indexing points, but at the moment you want to index shapes, then there's only one solution, or actually two, that can support that. Do you need to support a variable number of shapes per document or not? So there's various questions here that will guide you to different solutions, or using multiple solutions together. So a key abstraction in Lucene Spatial is that there's a spatial strategy abstraction, and you give it the shape, and it will give you a field that you add to the Lucene document for indexing it, and it'll also, hey, here's the shape, give me the intersection for the index document, so tell me which document matches this shape. So it kind of hides, it's a black box, and it figures out a lot of the details. And there's 4 or 5 actual implementations out there, and I'm going to talk about each of those. So I'm going to start with the simplest one. This is point vector, and it's basically what Solr's lat long type is doing. There's an x and a y. You index 2 fields that's both 2 doubles or 2 floats, whatever, and it behaves in the same way. The reason why this was, I think Ryan developed this piece, Ryan McKinley. On the Solr end of things, you would just use lat long type. You wouldn't bother, because that's why there's no adapter on the Solr side for this. But if you're a Lucene user that's not using Solr, then this is a decent option especially for small data sets, and especially if its restrictions are okay with you. Only 1 value per document, per field. It does use the field cache to put all the points in memory, which is not necessarily a big deal in and of itself, worth noting. Then there's the bounding box strategy. This one's kind of cool. Ryan McKinley ported this from Esri's GeoPortal, and the idea is that you're indexing bounding boxes. But the cool thing about this strategy is that it has some nice relevancy ranking. Because imagine there's some little diagram on the side where the idea is that you have different overlap percentages between your query shape and when you're indexing, and you might want, if you have a perfect match, then maybe that's up high in your relevancy, but if you have a shape that you barely overlap, then maybe that's low. So it's kind of cool. You can do some interesting stuff with this. And another point here is that you can mix and match these things. Like you might use this for relevancy for spatial, but then you might use only for relevancy, and then you might use another spatial strategy that's just for filtering. That's a very valid use case. So 4 doubles and 1 Boolean. Some people ask me, what's the 1 Boolean for? It's whether there's a world wrap or not. There's a logic in there about how to handle that. Okay. Yes, that's cool implementation. This implementation, by the way, bounding box is only on Lucene trunk. It's not in the 4x branch. It would port cleanly. It was just a matter of how tested it was, and it didn't meet my standards of testing. So it's there, but it probably works, and it was ported from somewhere else. So it's not overly complex, so it's fairly approachable. Then there's JtsGeoStrategy. Now, this one is very much a proof of concept. Ryan also developed this one. This is basically what this thing is doing is, first of all, it's not in Lucene's code base because it can't, because it fundamentally requires JTS. So this is one of those things that's sitting off in the spatial Solr sandbox area. And what this thing does is it actually, in JTS, you can index the binary representation of the WKT. It's a bit more compact. And in Lucene, you can put that into what's called a doc values, which means that you can ask Lucene, for this document ID, read me this binary chunk. And then, of course, you can parse that chunk, and then you can do interesting things with JTS operations. So in this case, you can use the full power of JTS. JTS is really powerful. There's all sorts of interesting, like if you need to support touches, the different types of intersection, you could possibly get there using this strategy. This is very much, though, a proof of concept. I would never recommend actually using it as is. It's more of a partial work in progress, partial proof of concept to kind of put some things together. But the way it's implemented is it's total brute force algorithm. Like you do any kind of search, and it's going to go through every single document, read each one in memory, and then determine if it fits or not. It's just not scalable whatsoever. But it's interesting. Very experimental and mature. Then the prefix-tree based strategies, and I have a whole section for this because I think it's the most interesting. So there's a recursive prefix-tree strategy, and that's a mouthful. In hindsight, I might have better named it grid field, something like that, tile, or I don't know, something like that. The word prefix-tree is synonym for trie. So whenever you see trie, T-R-I-E, that's the same thing as prefix-tree. It basically means you have you can imagine it as a sorted list of strings, whether it be character or binary base isn't the point, but they logically form a tree structure, but they're sorted. Probably not describing that and doing it good justice, but anyway, so the key point here is that you break down the world into a sequence of grids. I have some pictures on that in a little bit. There's a couple different grid implementations. There's one based on geohashes, one based on quad tree. The picture up there is a geohash. It's definitely the most mature strategy to date. I test the I don't say swears on here anyway, but I tested a lot. I tested a lot. I randomized lots of random testing. For those that have followed some of the stuff I've done with Solr 2155, this is sort of the evolution of that. It's the core intersection algorithm is the same, basically, and I've added on to it. So what are the characteristics of this strategy? What makes it good? Well, it indexes all shapes, not any shape that implements the shape interface. That being said, it does approximate all shapes to some kind of grid. So it is an approximation of the shape, and that the level of approximation may be good enough for your needs, but it might not be if you need a really precise representation. If you need a meter level precision of a state, that's just not realistic. But in practice, it works for folks. It supports a variable number of shapes. And you can furthermore query by any shape as well. Polygon, I don't care what kind of shape it is. Query by anything. With a variable precision, so you can configure the amount of precision you care about. Like just because you say, I want a point radius and my radius is 100 kilometers, I mean, do you really need it to 100 kilometers and absolutely no more centimeters? I mean, most people have a certain buffer amount beyond that they actually meant. So you can configure that. And just recently in Lucene 4.3, I just recently finished adding within, contains, and disjoint support. And the 1 week, well, on one hand, this field type does support multi-value distance sort. So if a shape has a variable number of points, excuse me, if a document has a variable number of points, you can find out the closest document from a given point. Okay, this is the only field type that can do that. On the other hand, the implementation is honestly poor. It won't scale very well. So I wouldn't say don't use it, but use it within a certain understanding. Like if you have many millions of points, if you have real-time search requirements, the implementation doesn't work so well. This is obviously an area that needs some improvement. Yeah. The bottom line for this is that it's really fast, scalable spatial filtering. And it doesn't need, with the exception of doing distance sorting, for just for filtering, it doesn't need any caches. It doesn't need any memory special caches to do that job. And I was talking with Ryan. I don't think there's any other search platform or NoSQL platform that has these kinds of advanced spatial features. Many platforms have index points and sort by sort, or they may have a polygon query, but you can't. I don't know of any other search platform, or NoSQL platform where you can index shapes and then query by those shapes. So that's pretty exciting. Obviously in the recursive, obviously in the relational database world, there's some very mature spatial products. But the moment you get into relational databases, that's a whole can of worms that have their own constraints and appropriate use cases. So it's pretty exciting to me. So if you want to talk about how this stuff works, let's talk about geohashes. A geohash is just a way of encoding latitude and longitude in a string together. It basically interleaves the bits from the latitude and longitude together, and for every sequence of bits, it just has a letter code. It's pretty straightforward. The Wikipedia article is pretty good. From time to time, I refer back to it when someone asks me some question about how precise is a certain level. And for Boston, DRT2Y is a particular geohash. If you ever want to play around with these things, this is a kind of cool site. You can go there and put in an address. It'll tell you what the geohash is. It'll show you what the nearby ones are. It's a little Google Maps mashup by David Troy. So if you break up the world at the top level, at level 1, as I call it, you break up the world into 32 grid squares. The only reason why there's some stretching going on has to do with the way the map is projected. And if you add one down, back and forth, that letter D for where Boston is, you start with letter D. Then you have this grid, you go letter R. As I keep going, you may notice that the grid flip-flops back and forth. That's just an artifact of the way the geohash, it has an odd number of bits per level, so it kind of flips back and forth between the orientation of the rectangle because it's not even. And there we go. So one of the things about geohash is, if you read this from the Wikipedia article, is that it was introduced as as something friendly to put in the URL, not as a indexing, encoding, or anything like that. However, it has good properties for spatial indexing because breaking up the world into a sequence of smaller and smaller grids, that's some really nice properties there to build off of. I have no particular love for geohashes or anything. It just happens to be out there. It's readily available. This is a Google Summer of Code project. The students signed up for it, so I'm really hopeful and excited that we'll have a more optimal grid implementation for spatial indexing. It will not have the use case nice and URL, unlike geohash, but it will be a great backend. Let's do a quick demo now. So I'm going to show you something in a little bit after I read off the slide. If you were to index using a quad tree, so the quad tree is not the geohash one. There's two choices. The quad tree one, the geohash one, first of all, is strictly geodetic. Like if you wouldn't use it for the temporal use case, interesting use cases. The quad tree, on the other hand, will work in both geospatial and in non-geospatial kind of scenarios. And it's pretty simple. At each level, there's only 4, A, B, C, D. So if we look at only a depth of 4, then A, AD, ADB, ADBA, those are 4 terms right there. Imagine that those 4 terms are being indexed for a point. So if there's one point that you want to index to whatever precision that would be for only 4 characters long, pretty weak precision. But in any case, it indexes every, this is the left edge n-gramming, those of you familiar with Lucene. It indexes at all of those, at every parent level. You get the parent grid, if you will. And this enables some really fast filtering algorithms that can then, that use only the parent levels. That's why you're indexing every parent. So if you index, so for a single point, the overhead is pretty low. Level of 4, then you basically have on the order of n, whereas n is the length of your string in terms of how many tokens there are. But if you have a shape, it has to basically decompose that shape. I had a picture earlier of Normandy off France where you could see the big grid cells and the smaller ones. So if you index some polygons or any shape that's not a point, you basically have a lot more tokens. And so we see the parent at the A level, AB, ABA, and then you'll notice I index, there's a little plus symbol at the end. So if you're indexing shapes, I add a token at the end to indicate that the shape ends at that spot in the grid. So I need to know when it stops, when the shape ends. For a point, it's a non-issue. It always goes down to the bottom. But for a shape, you need to know when does it stop. In other words, if there's that big cell in the middle of France, how do you know that there's no shapes beneath it? So there needs to have a little plus right there. In the process of putting the slide together, I realized, okay, I looked at all this, and I said, oh yeah, I indexed not only with the plus token, but also without. So there's a lot of terms that are indexed. It's almost, I'd say there's probably a 40% overhead by indexing the terms twice. And that's actually, the moment I saw that, I'm like, ooh, we can probably remove that. That's probably an improvement that can be added in the future that would reduce the total number of terms by probably 40% for indexing non-point shapes. The reason why it was done this way is that the particular search algorithms are expecting them to be both. I'll do a quick demo to make it interesting. Now if I go to, so on GitHub, I went to Solr Spatial Playground. I built it a long time ago. On the command line, it's a Maven-based project, so JD:run, I've already built it. Already checked it last night. I did the -o flags. I don't want it to re-download the latest snapshot of Lucene and potentially break in the middle of a demo. I think it's up. Now, this web app, by the way, is purely for like fooling around for me and Ryan as we were working on stuff. At times you want to try some things out. It's not for, that's all it is. It's just for fooling around. This interface will come up here. The very first time it comes up, you'll see nothing down. You will not see this stuff at first, but it has a button called load. So you would hit that, and it would go index all these things. It takes a long time, but just because it takes a long time doesn't mean in your application it will. It takes a long time because it's indexing every polygon and shape in like 5 different ways to experiment with different ways of indexing. So there's a lot of overhead that's there purely for fooling around. And in fact, you'll get an exception in the stack trace, and it'll say ATA poly, it'll blow up. ATA is Antarctica. Antarctica wraps a pole. Pole wrapping is not supported. That's why you get an exception for that. Now, if I go to the playground link at the very top, you might easily miss that link. This is some cool stuff you can do here. So if I pull up, there's different ways of doing it. You don't have to name it. I can call it, don't worry about the name. You can either enter in WKT right here, or you could just pick it right from this list of existing countries. Let's go to Fiji. Fiji crosses the date line, so why not? Kind of like Fiji. We'll do geohashes, do KML, 16 depth, yeah, distance 0%. I'll get into that later. Submit. Good. And Fiji. I love Google Earth. That is a very coarse-grained That's a very coarse grade. Let me see. Why am I was expecting something more detailed than that. Of course, this is the demo, right? I didn't run this right before, so that's what I get. I was paying attention to the keynotes in the morning, so maximum did the error percent. Why is it that low? Oh, maybe because the maximum depth is too. Well, I don't know. Let's do France. It's not the datelet. There's no bug there, so I know of. I just. Oh, thanks. There we go. France. Okay, I think it changed it. Came out. Submit. Ah. So it's kind of interesting. You can go to the coast and get a sense of how detailed it is. And you can see how many levels are involved in it. This is something to play with. It's neat to see what if you have a particular polygon in mind, and if you're this interface is useful for testing, does your polygon even work? And if it does work, then how detailed is it for the parameters that you give it? Down here, I'll get into that in a little bit. Maximum depth, that means how many characters is the longest character down. And distance error percent is the, so I might as well describe it now. The idea is that for any given shape, just because I say the maximum precision of your world is a meter, if you're indexing this room, then a meter level is appropriate, perhaps. But if you're also indexing states, do you want the states to also index to a meter just because that's the maximum you support? See, ideally, it's relative to the size of the shape in question. So distance error percent is relative to, it's an approximation. So it's like the radius. If you were to take the shape in question, and even if it's not a circle, pretend it was, and what would its radius be? And if it's 2.5% of that, it's willing to extend beyond that, up to that amount. That's kind of basically what's involved. So if you wonder, like, oh, what is 2.5%? What if it was 10%? How if you wanted to play with it, this tool is kind of useful for that. Okay. So the architecture here, and this has worked fabulously well, I must say, is this separation of concerns, that a shape only worries about being a shape and calculating relationships. That's it. That's all shapes do. And then there's something called the spatial prefix tree, which is a class that divides the world into, it might be, I have 4, it might be a quad grid, it might be a geohash grid, it might be some grid that no one's the shape doesn't care. The shape is just asked to intersect with the given rectangles. The spatial prefix tree must know how to go back and forth between a byte string that will ultimately come out of Lucene, say, and these cells. But the cell is really it's a rectangle, basically. And you can ask a cell for its subcells, etc. Then but that's not search. It's just a way of decoding a shape into a sequence of grids, smaller grids. That's all spatial prefix tree is. If it had a better name, it might be spatial grid. I recently renamed the node to cell because I think cell better evokes the spatial nature of it. Then there's the prefix-tree strategy, which is fundamentally where the actual indexing and search algorithms are. That's where the cool stuff is, I think. The actual recursive prefix-tree strategy doesn't actually have that much code in it. It refers to the prefix tree to decompose a shape into a bunch of cells that then get indexed. That's pretty straightforward. If you do an intersects, if you do contains, if you do within, those are all separate classes that all have recursive algorithms that decompose the world in a recursive way, top down. It's tremendous fun working on that stuff because it's very algorithmic and thinking about how to make something that scales. Intersects scales fabulously, contains scales very well. Within, it works, and there's a to-do to ways of making it scale better. The within algorithm. And there's also disjoint. I didn't put it here on the slide because disjoint is universal, because disjoint is simply the inverse of intersects, with one caveat, is that there has to be spatial data in the field, because if your document has no spatial data, none of these predicates will match it. So aside from that, And the prefix tree is this is working well because the prefix tree doesn't know anything about any particular shapes at all. It just knows it's getting a shape, and it knows it can talk to the spatial prefix tree implementation to decompose that shape into cells. It doesn't even know about geohashes or quads. It doesn't know anything about that. It just knows that it can talk to a cell from the grid and decompose it into other subcells based on a query filter. And it could be a 256 area cell. It could be a tree that has 256 at the top level, but then has 16. It could be anything, and the filter algorithms don't care. They don't even know about that at all. So these abstractions have worked very well. I mean, of course, at times I think, well, maybe this method should be named this or that, or add this operation here or there. But the separation of concerns here has worked extremely well. And these prefix tree strategies, this is where the rubber meets the road, where the search actually happens. So basically, it talks to Lucene's term enum, which is where you're actually iterating over the actual index terms and then seeing what documents match it. And it's basically populating a big bit set. So if this was a deep dive, I would go further and talk about, let's say, how the intersects one works. I think it's quite interesting. At a high level, I'll say that you take the query shape and you figure out at the very top level of the grid which cells intersect the query shape. Okay, but if you get to one of those cells, and you might find that because it's using the terms enumeration, it may find that there's no term there. There's nothing there. So it stops. The recursive algorithm will stop very quickly once it finds that there's no data there. So what this means is if there's like Hawaii, right, and there's ocean around it, and you got no point data outside in the ocean, let's just say, but you got a lot of stuff on Hawaii itself because there are businesses there, let's just say. If you do a circle query around Hawaii, that will work really fast because it will very quickly grab all the stuff within the middle big cells of your circle, and towards the end, there's nothing there. So that'll be super fast. Things get slow when the very fine edge of your shape has lots and lots of stuff, lots and lots of index stuff. That's when it starts getting slower. So it's kind of a high-level view of looking at it. It also is there's two phases to the algorithm. There's a recursive decomposition, which is very scalable and sound and good. But the reality is that, especially if you look at, say, sorting algorithms, there's a point where you get to a small enough data set where what scales in the large, there's faster ways to do it in the small. So once you get to a small square, I think by default it's 4 levels up from the bottom, it just iterates over all the points there and then intersects it with your query shape. So at that point, it's faster to simply iterate over whatever may be there than it is to recursively decompose your query shape into smaller grids. So here's a little sample code about how this works. We have so a little bit of spatial for J in the beginning. We have the spatial context. I'm omitting some spots here and there. It was hard to get everything readable on one slide. You initialize the spatial strategy. For the recursive prefix tree, you tell it. And at search time, you make a filter. You could also make a query from it as well if you'd rather have that. And in the case of the recursive prefix tree, many of them are implemented in terms of the other. So it depends on what you're looking for, a query or a filter, but it's non-scoring by default. And in this case, you create what's called a spatial args, which is you can think of it as the command pattern. It takes the predicate, like intersects, contains within, and the shape in question. And finally, you search for it. What we don't see here is sorting. I didn't add that. There's another method on spatial strategy called make value source. And a value source is a way of getting distance values per document. And then you can sort by it, or you can use it in a relevancy if you wanted to, stuff like that. So a couple things I want to highlight about what's going to be added in the future. There really needs to be a better distance sorting, a better cache for the prefix tree. There's a couple implementations I have in mind, actually, one of which is based on memory. There's another approach where at the very same time that you're doing the intersects, you could also calculate the distance right then and there for every point that you see. So if you have a smallish shape where you're only going to match, your query shapes are only so big, and you're only going to match so many documents that could possibly be there. If it's not that big, then it may be the benefit there is that there's no cache you even need. You don't need to put them on memory because at the time that you do the intersects, you right there iterate over all the points that you find and then figure out which one's closer to the query point. That's one implementation I'm thinking of. And I'm excited about a Google Summer of Code project that's starting, where I'm going to mentor someone in Sri Lanka, I think. I should say that's tentative, hasn't been announced yet. There may be another person who vies for the spot. But anyway, I'm excited about that because that'll raise the performance even greater. What there really needs to be is a better benchmarking. What there's really lacking is benchmarking. And it stopped me from making certain advancements because I wouldn't know where to put the tuning value to, because without having a benchmark, how do I even know where to set certain knobs? So there really needs to be, at one point in time I did benchmark it, and it did really well at the time that I did it, and that was 2011. What else do I want to say? Another interesting problem that I think is very useful for people is that some people, it's all well and good that these shapes are approximated to a grid, but what if you want to do an exact search, exact to very high fidelity? It's not really scalable to index every meter level of Massachusetts. Let's just say you had an accurate polygon vector for Massachusetts and you want to get it more accurate. I think there's a way of using a combination of the current recursive prefix tree approach with the JTS strategy that actually puts the vector in the index itself. Because you can imagine a clever strategy that's able to look at the grid approach that only goes down to a certain level of approximation. And it can know right away that these documents are sure to be intersect. But these, I don't know, it's on the edge. It maybe not. So only look up those to see if it's an exact match. So I think there's some options. There's definitely some future for actually implementing exact match. It's not on my radar at the moment, but I'd love to work on it, and I have an idea how to do it. OK, so the Solr side. The Solr side is really a fairly thin adapter on top of all the work that's happening now under the hood. But first, if we're talking about comprehensively about spatial, I should talk about lat long type, even though I didn't write it. And so this came out in Solr 3. It was not based on the Lucene Spatial contrib at the time because it was fundamentally broken. And there's basically a lat long type and point type depending on whether you want something geodetic or Cartesian. One of the nice things about it that I recommend doing, it's a perfectly valid field type. I don't want to put it down or anything just because I'm working on something newer and better. It's better in many ways, but this scales very well for smaller data sets because it's so simple. It's very optimized. A lot of tricks are done in there to minimize the amount of code involved that happens on a per document as it works. So in the small, I think it'll scale very well as long as it meets your requirements otherwise as well. One nice thing that you can do that I recommend doing is by default, the schema will use lat long type and it will say coordinate. It'll allow you to pick the type of field that actually implements the x and the y, the lat long. I recommend actually changing it to a float because unless you need better than 2.5 meters, why not use half the memory? If you need better than 2.5 meters or something like that, well, okay, then use a double. So Solr 4 Spatial is a field type. It's a mouthful. I apologize. At this point, maybe it's set in stone. Sometimes I abbreviate it to just RPT for recursive prefix tree. That's the significant part of it that's relevant. You set what's called the context. Remember the .geo, spatial context.geo. That's if you want the JTS. If you need polygons, if you need WKT, then you basically need to use the JTS, which means you also need to add JTS to your class path. But otherwise, you don't need to set JTS. Just because I put it here doesn't mean you need it. If you don't need polygons, then don't. Just some key things here. Dist error percent. That is the default approximation for a shape. I remember I mentioned thinking of a shape, approximating it as if it was a circle, even if it's not, and approximating how accurate you want to represent it. That's what that is. That's the default, and that always applies to every index shape. It's a non-issue for points. Points are fully maximum. But if you're indexing shapes, then that applies to that. If you're also querying by a shape, it defaults to that. Although at query time, you can actually pick maximum precision. Because if you want a big circle, but you want it to be as accurate as your grid actually has it, you can do that, and that's fairly scalable. Max dist error is where you actually specify how accurate, what is the minimum actually you need to, or max depending on where you're looking at it, is how accurate does this thing need to be. Because all the units are in degrees, you specify in degrees. That right there, by default, it ends up being close to a meter by default. And of course, if you don't need that level of precision, definitely change it because you'll get some performance benefits with that. Indexing is fairly straightforward. You just give it latitude, conjugate longitude, or x space y, or you can give it WKT. I want to move along a little faster because I only have 10 minutes left. So what I added in 4.2 is the bounding box, geofilt, Solr query parsers, or actually I added support to that so that you can use those query parsers. It's much more convenient, especially if you only have to query by rectangles or circles, then definitely use them. And the D equals 5. That's actually 5 kilometers within this. When you use geofilter bounding box, then the D parameter is kilometers, even though you say units equals degrees in the schema. You can also do range query style for bounding box too. If you need more advanced ways of articulating your spatial search, then you probably need to use the one at the bottom. Geodist does not work with the new field type. I'm thinking of actually adding it. It's been it'd be a bit of a hack to make it work, which is why I haven't. But I think I've realized that people want something that works in the same way, even if it's a hack under the hood, then so be it. But it doesn't yet. So basically, the query itself returns the distance as the score if you ask it to. So if you look at the local param, score equals distance, in that case, you're telling it to return the distance as the score for that query. And then you can do things like use it in relevancy if you want to, or sort by it. It can be a little awkward, to be honest. Distance faceting, so if you want, if this is a case where we're showing up to 10 kilometers, up to 50, up to 100. In this particular example, they are overlapping. I personally find that more useful. I hate it when I go to a site and I'm giving these little narrow ranges where I'm willing to drive up to 100. I don't care 50 to 100. So anyway, so you're seeing that right here. It's pretty simple to use the field type with geofilt for doing a radius-based distance faceting. I want to move past future in the interest of time. I already did a little demo. Interesting use cases. So this, I grabbed a picture off image search, Google image search that shows something that looks like what I'm trying to represent here. You might call this heat map. You might call it grid faceting. There's actually a JavaScript library that can take a grid of values and smooth it and make it look really like you have more fidelity than you actually do. I think it's called heatmap.js. It's pretty cool. In a few of these cases here, full disclaimer, like these things should absolutely work. I have no reason to believe that they won't work. That being said, I haven't needed to use them in my day job. So a little disclaimer there. But in each of these cases, someone has used them and said that it works as I've described it to them. So if you want to produce pictures like this, then there's a couple ways to do it. One is at each geohash level, you create a field that has that length. And then you figure out at what level of granularity do I want to show a grid. And then you do a facet on that particular field. And it's only going to show those in that area. And then you might get graphs that look like this. I would love it if, I thought a while ago that this would become a priority for me, but it just simply hasn't been. But I'd like to, it'd be cool if there was a Solr component or request handler or something where it would handle a lot of the details for you. That way you could simply say, hey, I want that grid, and I want it to be, here's the boundaries of my grid, and I want it to be this kind of precision. You give it some sort of number, and it would give it everything back. That would be cool. Doesn't exist yet, so you have to do things semi-manually yourself. There's different ways to tune this stuff, too. Yeah. Plotting lots of points on the map. So I'm working on a project where we do this, and I cringe when I see it because it's almost like using Solr as a database, and it's not. It's not. If you want to say, if you get lots of results back, you might be showing only the top 10. But if you're showing a map, you probably want to show all the points. But that means potentially, at least the basic way to think about this is, oh, I guess I need all rows. But that's potentially slow. And if your documents have a variable number of points, as in the case in apps that I work on, you don't even know how many points that is. I mean, one document might have 1 million points, hypothetically. It doesn't happen, but it could be a lot. Or you could theoretically have 1 million documents all referring to the very same point. So one way to look at this is to instead solve it using faceting. And in that case, you can tell it exactly how many distinct points that are going to come back. Because you can really you can limit it that way. You'll know how many you get back. You'll get no more than 1,000 if you say facet limit equals 1,000. But you have no idea how many points you're going to get, no matter how many rows you ask for. It's hard to know what the memory requirements actually are until you try it with your data, because everybody's data is different. This might not scale if you've got sensor data coming from people's location and its overall time. I mean, there's obviously limits to what you can do with this. And another thing, do you really want to? This is a snapshot from a project internally I work on, and we call it screen barf. And for some reason, my project leader loves screen barf, and I say, why? I'd rather see a heat map personally, but I don't know. if you're saying facet.limit equals, really think about. You probably want to think about this in terms of how much is too much, and then splitting the user experience into two approaches. Where if it's only a few points, I want to see exactly what those points are. But if it's like this, that's not useful. Yep, we show it. This is an interesting problem that I saw on Stack Overflow that I really liked. And it was not posed in this sense, but this is the way I like this question. It's easier to think about it in this way. So imagine where you're searching for compatible two parties, where they both have a distance that they're willing to travel. And they need to be mutually overlapping. So there's no, hookups in an intermediate state. There's got to be, they got to both be willing to drive to each other's place, wherever that is. And this is using a dating site here. It could be like a contractor with a certain range that contractor is willing to drive to do a job, and you might have a certain distance that you have requirements for. There's different ways of looking at this other than a dating site. So for the current user, you want to find someone who's not too far, but you also want to find something that's not too far for them. I don't want to use up too much time in asking you guys to answer these questions. So instead, I'm going to tell you the answer. So you index each user's location. So you have two spatial fields that each address both sides of this. So you index each user's location as a point, and then as a circle in the other field for how far you're willing to go. And then you combine these two. So here on the left side is you index everybody's point, and then you search for a circle, and you find everybody that's close enough to you that satisfies your constraint. But then the right side, you need to make sure that you satisfy everybody's constraint to get to you. And here's the interesting case that Hausman, Chris Hostetter, was talking about on the Chump the Stumps. I'm losing it. So this is a really interesting way of looking at spatial that's not in the geospatial sense at all. One thing that Lucene has not been able to do either is index durations. Although I will say that with the new spatial support for indexing shapes, you can represent a shape as a rectangle with no height. You can who cares about y? Just x. That's another approach to thinking about this. But this way of looking at it is where I have a picture on the next slide. In fact, maybe I'll just jump to that in a moment. But what won't work is having two fields for your start time and your end time, and saying both of them are multi-valued. On any one document, you'll be able to look at that document. As a human, you might look at that and say, OK, you recognize the starting. You see that they line up. It looks good. But when you try to actually search it, they don't line up. So you can't solve it that way. And there's different use cases for this. Hotel room vacancies or movie show times was the first case that I've heard it. Someone was telling me they have certain price ranges, multiple price ranges. That's interesting. Different use cases. So instead, you model durations as points, where the x is the start and the y is the end. So all the points naturally are above the horizontal line. And in general, they tend to be somewhat close to it, because if you start at a certain time, it's only if the average duration is within a certain distance, then it's all going to be kind of above that. And so depending on the nature of your query, like, do you want to find if each of these points represents a shift, let's just say, depending on the nature of what you're looking for, your query rectangle looks different. Do you want to find all shifts that completely are within a given bound? Or do you want to find all shifts that overlap in any way? Or do you want all shifts that overlap my query shape, depending on what you want? Did I put the link to the wiki page on this? I didn't put it here. There is a link to this approach with more detail. But basically, you configure the field, you say geo is false, this is not geospatial. You give it the world bounds. This is where you do need to give it, you need to figure out what is the unit of, you can't just give it timestamps. Sorry, it won't work that way. Even nice if it did, it doesn't. So you have to come up with some sort of unit of time, like an hour, I don't know, whatever that is. And that's your unit of what 1 is, 1 hour, let's just say. It might be a minute, whatever your use case is. And then you define the bounds as 0, 0, and the maximum time into the future that your search space extends to. You might need to reindex from time to time with this scenario. And you want dist error % is 0. You want maximum precision. This is not some sort of geospatial search where the search radius is, approximate. No, you want it to the very end. And max dist error is 1. Depending on the nature of your queries, it may be 1, maybe 0, maybe like a half, depending on how there's the chump that stump. He stumped the chump. The questioner asked basically he didn't want to query the very end, so you might need to, I said, unbuffer that shape by like a half on either side. So you might end up having a max dist error actually of like 0.1 just to be safe or something like that. And you always say intersects. It sounds a little funny because when I want contains or within, but there's some clever ways of looking at this in terms of this in this way. It always ends up being intersects. But where you put the numbers, there's the beginning of your search range, the end of your search range, and you put them in different spots of that rectangle depending on what it is you're looking for. Yeah, I won't scale to a full precision. I think the approach is overall scalable, but you have to have a window out. So I mean, it's not going to be millisecond precision out to years and years and years. You have to make it more boundable. I honestly don't know how scalable it is in terms of, I'm not too sure, but I think in terms of how far out to, in terms of how big that number is, I don't know how scalable it is. But in terms of the search would be very scalable. Because if you look at these rectangles, the way the recursive prefix tree works is it only really does hard work where there's actually data. So it's only along that horizontal line where there's some stuff. So it'll work hard to decompose the rectangle again and again and again to get to figure out where data is. But the moment you get to that top rectangle, it doesn't even look there really. Thank you.